Welcome to the Fairewinds Energy Education podcast for Wednesday, July 10th. Today's podcast is accompanied by a video transcript as our recording quality does vary somewhat. My name is Nathaniel White-Joyal. Joining me today is Marco Kaltofen, the president of Boston Chemical Data Corp. And a doctoral student researcher at Worcester Polytech Institute, as well as Arnie Gunderson, chief engineer for Fairewinds.
Thanks for having me.
Yeah, I'm glad I'm here.
Marco, I had a chance to look over the report that you did on that sample from outside the exclusion zone around Fukushima. Kind of fill me in on exactly what you found from that soil sample.
Well, I think one of the things that's unique about this particular accident is that there's a lot of crowdsourced data. We've had a lot of people who have the resources to go out, collect samples, do testing, kind of explore their environment and get some data about what they're seeing. And we kept hearing reports about something unusual, a black dust that was on the surface of soils or streets that was much more radioactive than any surrounding soils. So it was almost as if some concentrated radioactive contaminant from the accident was pretty much refusing to disperse, collecting in a certain gully or gutter, and folks were getting it. So we finally got a very small sample of them, a tiny amount, really for safety reasons, and put it through a whole battery of tests.
Talk about this dark sample that has been showing up in Japan, and I realize that what you've got may not be representative, but it certainly is unique. And maybe what does it tell us? We know it came from Daiichi because there's cesium-134 and 137 in it. Is that?
We'll just back up a little bit. What we've looked at Worcester Polytech is a couple of hundred different soil and dust samples. And what we're doing with those samples is we are not just looking for the radioactive isotopes that you would expect from Fukushima Daiichi, but we want to know how big the dust particles are that are carrying that radiation, because that tells us how far they're going to travel and what process within the reactor created them and where they're probably going to end up. So we actually isolate those radioactive particles from our samples, and then we photograph them with a scanning electron microscope. So we learn a lot more about them than just using a Geiger counter or a gamma spectral detector.
Okay.
And I was going to say, what's different about this material is, unlike a lot of the soil and dust samples we've gotten, there's a real uniformity to this stuff. It's a single substance. It's not a mix of mineral particles and pieces of dead bugs and plant matter and dust particles. It's actually very homogeneous and uniform when you look at it under the microscope. And it doesn't look like the surrounding soils. And it is much more intensely radioactive than any other soil or dust sample we've gotten from around Fukushima Daiichi. So this material is different. It's not a natural soil. There's something unusual happening with this stuff.
So, I've been reading this stuff for years, and there keeps coming up these persistent stories of this black dust that winds up usually in places where there's a hollow. Apparently, something's washing out off of other surfaces and collecting. And it seems to be detected, as you said, because it's extraordinarily more radioactive than anything other people have been bumping into. Because it's black, does that mean anything, or is that just a coincidence?
Well, actually, it does mean something. We were able to put this material under the microscope, and these aren't simple particles. They're kind of, they're aggregates. You ever seen a cheese ball that Christmas rolled in nuts? It's a big thing made out of a lot of small things smushed together. That's what these particles look like. And they're all glued together somehow, and they stay cohesive. They don't fall apart when we handle them in the laboratory. And when you look at them under the microscope, it's as if you took hundreds of very small radioactive particles and glued them all together into different shapes and sizes. And that's what gives this stuff the black appearance. And that might be why it tends to stay together so well in the environment.
So it sounds like this stuff was created at Daiichi. I mean, it didn't go out as little particles and get and coalesce after it left Daiichi.
Well, while that's possible, one piece of evidence that tells us that's probably not the case is that it is uniformly radioactive. That means that the entire sample is radioactive. It's not a mix of normal soil that's non-radioactive plus a little bit of contaminant. When we take some of this black dust and we spread it out over an X-ray plate, it actually exposes that X-ray plate from its own radiation without any additional light or photons or X-rays. And every single particle in the sample darkens an X-ray plate. So there's nothing uncontaminated in these samples.
That's fascinating. We probably should give the listeners an idea of how radioactive the sample was. The person in Japan who sent the sample to your lab was walking along with a Geiger counter and found an area that was highly radioactive. He then got in touch with you and I, and because it was so radioactive, we asked for an extraordinarily small sample to be sent. And it was about 1/10 of a gram. And to give the listeners an idea of what a gram is, a gram is about the weight of $1. So 1/10 of the weight of $1 is the whole sample that we sent through the mail. And I'm going to ask you to pick it up from here, Marco, and tell what that 1/10 of a gram sample contained.
The entire sample is probably about the size of an aspirin tablet. And it was mostly beta radiation from the cesium-134 and 137 that it contained. And the total amount of that radioactive cesium was about 1.5 megabecquerel per kilogram. That means for every kilogram of this material, it would have 1.5 million radioactive disintegrations per second. Or for this very, very small sample, you could use a different unit. You could say it's 1,500 radioactive disintegrations per gram, and so on. But those are big, big numbers. They're much higher than anything else that we've seen.
And a kilogram is about 2.2 pounds. So about 2.2 pounds of this material would disintegrate off at about 1.5 million disintegrations every second, and then the next second, and then the next second. We're not suggesting that there were many pounds of this material, thank God. There was a small piece of land that was contaminated, and on that small piece of land, we got even a smaller sample.
Well, here's what's important. This material is not representative of the area as a whole. The sample was taken just over 10 kilometers away from the accident site. So it's just outside the exclusion zone, within the restricted zone. People can visit these areas for the short term, but they can't stay. What's happened here is somehow this material, which is much more radioactive than the surroundings, stays together and isn't dispersing into the environment. That there's some natural phenomenon that causes this material to collect and create this hotspot. And that shows the need for vigilance, because if there are natural processes that are going to allow hotspots to continue at this kind of concentration 2 years after the accident, then these hotspots need to be mapped, and people need to be aware of that potential for higher than average radiation exposure.
Well, why do you think that we're getting these hot spots?
Well, it's really all about the form that this radiation is in. The radioactive material that came from inside the reactor is attaching to particles that tend to clump together and aren't being dispersed. They're not dissolving in rainwater. They're not being taken up by plant life. They're staying cohesive, and they're resisting degradation. They're not degrading into smaller particles or simpler things. And the thing that's also interesting about this is that there's not just the cesium that's in here. We also saw a good deal of radium. The sample had fairly high levels of radium-226. Now that's not a radioisotope we heard much about. The radium-226 was almost as active as the radioactive cesium in the sample. Radium-226 is a degradation product of uranium. We can't really detect the uranium directly. Uranium has such a long half-life, it doesn't really show up on the gamma detector. That's why the uranium that was created when the Earth was created billions of years ago is still around. But one of its daughter products, one of the things that degrades into, is radium-226, which is much more intensely radioactive than the original uranium. And this tells me that this particle contains not only fission waste products from the reactor, but very likely contains a concentrated, unburned nuclear fuel. And that's unusual. This sample had by far the highest level of uranium daughters that we've seen in sample. We're actually seeing material that might well have come from inside the fuel sample.
Okay, when I hear that, that's clear evidence that the containment was breached. The interesting thing to me is when I hear the black, I think of like algae or fungi or something like that. But you're saying this is not an organic substance, is that right?
No, it's not an organic substance. It's a mixture of very small particles, and just the way they aggregate gives it the appearance of being black, but it's probably, I won't say optical illusion, but it's an optical effect of the size of the particles and the way they're going together.
So can you talk a little bit about the issues that are going to be, why people are still being allowed into the areas where we're seeing these radiation hotspots, or can you talk a little bit about what effect that might have on people who are exposed to these?
There's nothing about the imaginary line between the restricted zone and the exclusion zone that can stop this material from being transported outward to where the population still is. So I can't speak to any kind of government policy, but I can say that this material obviously doesn't respect the political boundary or a regulatory boundary. It's going to move wherever surface water or wind is going to take it. The particles are a little big to move easily by wind, so it actually take a fairly strong wind, but obviously that happens in any given spot sooner or later.
So these particles are heavy enough that they're not going to travel across the Pacific on their own, but they were light enough to be thrown, 10 to 20 kilometers away from the accident.
Well, this sample came from about 10 kilometers away. If it could get 10, maybe we could look further afield and find this again. I know we've heard reports of the black material much further away than just 10 kilometers. What probably happened is that originally they were very small particles that travel very easily and can travel long distances, and then they somehow aggregated. This is actually a common effect with radioactive particles because they give off alpha and beta radiations, which are electrically charged, and it makes the dust particles that contain them pick up an electrical charge. So they tend to seek each other out and aggregate. Very normal. This is just an extreme case where we've got very large, very radioactive aggregates that have formed from these small particles. And given that the testing showed that we saw uranium daughters, cesium-134 and 137, with the signature for Fukushima, and a lot of materials that are suspected fission products, obviously it's very likely these aggregates contain at least some particles that came from inside the reactor.
Are these particles light enough for people to ingest them or breathe them in?
Well, certainly they could be ingested. They could be, the amount of hand-to-mouth activity people, even adults, engage in is pretty surprising to most folks. And certainly for children or anyone working with soil, agricultural workers, construction workers, ingestion could be a very serious way of taking this material into the body. Inhalation, breathing it in. Well, these particles right now are too big to be breathed in, but if they aggregated, they might disaggregate. And in that case, they could be a breathing hazard. But right now, I would see they're much more an ingestion hazard. And that usually tends to target children and agricultural workers.
I remember last 2 Octobers ago, you did a paper for the American Public Health Association, and you had photographs of kids' sneakers. So I think what you're saying is that this could be, this is the kind of stuff that can wind up in a kid's shoelace and then on his hands and then in his mouth, but not likely to be inhaled.
Less likely to be inhaled because of its size. The thing to keep in mind is we had a 100 milligram sample, and it was hot enough to get the health institute, the WPI, very interested in the sample. A child, on average, consumes between 100 and 200 milligrams of soil a day because of hand-to-mouth activity. So that's something to really think about.
Wow, that's breathtaking. Yeah. So, it certainly behooves authorities over there to continue to look in areas that may have been cleaned up already, because this stuff, as you said, has will migrate and knows no political boundary.
There are a lot of ways where we can model and predict where material is going to travel. That's why we're excited to have a sample of it, because now that we know the particle size, a little bit about the density, we can make some better guesses about where this material is going to end up. And let people at least have the option of cleaning up a little smarter, and maybe targeting places where this is going to become more concentrated and obviously be a bigger hazard.
Well, so I think this is a great opportunity for us to kind of talk about solutions and how they can start to clean this up. What can we do to get rid of these particles in these hot spots?
I've been a civil engineer my entire working life, and there are so many technologies for cleanup and for remediation, and this has been done in many places, often quite well, and it's become routine in construction, development, real estate transfer, take care of these kinds of issues. But what always has to happen first is there has to be a top-down approach where we actually mandate that these issues be addressed. So we're getting into the area of policy. The technology and engineering is absolutely there to have an effective cleanup. All that has to happen is that people need to demand it, and governments need to back up those demands.
I have been saying since last year that that the Japanese government really, to fight a big problem, you need to admit you have a big problem, and I've never seen the commitment to admitting that it is a big problem, and they seem to be nipping around the edges, but not really going after just realizing how tough this problem is to begin with.
Well, I can't speak to Japanese government policy. I'd be a fish out of water there. But I can say that this is not a problem that you nip around the edges. This is a problem that requires a comprehensive solution. And we have done this before with good success. We've dealt with lead, for instance, in the environment. Lead used to be a scourge of our children. It was probably one of the largest public health hazards we experienced. And we have, as a country and internationally, dealt with that problem and dramatically reduced exposures. It was top down, backed up by good research. There's no reason we can't do the same thing with the Fukushima contamination.
Marco, this is the second time in 2 weeks where we've heard that exact same problem about this is a solvable problem, but you have to really be committed to thoroughly implementing the solution. There's a report on the Fairewinds website on the Demystifying Nuclear Power blog on the site, and it's written by a professional journalist named Art Keller, and the title of it is cleanup from Fukushima Daiichi, technological disaster, or crisis in governance. So if people who are listening to this want to read a little bit more on this topic, they can switch over to the blog and read Mr. Keller's eyewitness accounts of the difficulties American firms are having in attempting to clean up the site.
Is this an isolated sample, or is it more likely that there are going to be more hotspots like this?
This is an isolated sample. You could take and do some statistics on how often we're likely to see samples like this. If you do it based on the samples that we have, which are obviously selected since they come from volunteers, I mean, we're talking about this sample is in the top 1%. So it is strikingly concentrated and intense, and fortunately somewhat rare. It will obviously take much more comprehensive testing to find out exactly how many of these small hotspots could exist. One way to do that is for everyone to share their data so that you can compare and get a little more statistical power, because you're combining everyone's samples and doing your review.
It's rare, but it's not unique. There have been reports of a black powder that's highly radioactive for more than a year, in the relative nearness to the plant, less than 20 kilometers or 12 miles. But this is really the first one that we've been able to analyze in detail. And I think what makes this unique is that we've got a small piece in the lab, and are really amazed at the isotopes that are in it and the concentration of the isotopes that are in it.
We were lucky to get the sample. We've been hearing about this type of material for a long time now, and I'm really pleased to have had the chance to analyze it. There really can't be any doubt about where this material came from, and I'll be honest, I'm disappointed to hear that it's not unique. But that makes sense that this kind of material would have escaped given the severity of the accident.
Thank you both for taking the time to join us today.
Yeah, thank you for having me, Nat. The one last thing I'd like to add is the fact that we were contacted by someone in Japan who we then put in touch with Marco Kaltofen, and we knew this sample was coming. It's important, if you have something that you think is scientifically interesting, to send us an email before you send the sample. We have a sampling protocol that we would send out, and it just makes sure that when the lab gets a sample, we're aware ahead of time that we can handle it safely and appropriately. So to the people in Japan, especially Fukushima Prefecture, there are many samples we would be interested in analyzing, but please contact us first, and let's make sure that we abide by the protocols we have in place to make sure the shipment is safely shipped and that you're safely protected when you take the sample in the first place. Thanks again for listening to Fairewinds.
All right, bye, everybody.
This podcast has been a production of Fairewinds Energy Education.
We need to get subscribed and get this unity stronger and beat YouTube at their own game. Okay, that's what this is about. Like I say, go to the remix button, hit the remix button. That way you'll have this video and keep up with this. Otherwise, YouTube's just going to control us, guys, and it's really bad.